The next proof technique is proof by mathematical induction. Such a quite powerful technique, heavily used in the field of discrete mathematics, in particular in proving claims related to graph theoretic problems. And there is something called pigeonhole principle. There we come across this proof technique, and in the context of Ramsey theorem, and there are many counting arguments which one can prove using this technique, namely mathematical induction. And on the face of it, it appears quite simple, but it's very powerful technique. It has got three components. So proof by mathematical induction. So this proof, if you look at the way it proceeds, it has got three parts. The first one is called base or basis. The next one is called inductive or induction hypothesis. Some assumption, induction assumption or hypothesis. The third component is called induction step or anchor step. Induction step or anchor step. So as part of base case, we show our claim is true for some sample values. Say you are trying to prove a claim which has got some induction parameter, say n. And we say for n is equal to 1 or n is equal to 2, the claim is true. Then we make some assumption that we call it as induction hypothesis. And subsequently, by assuming this, we prove, and that component is called induction step. And together with all three, we say, once we establish a formal argument with these three components, we say our claim is true. So the way this technique works is one has to explicitly prove for smaller values, which we call it as base cases or bases. Subsequently, assuming the claim, or we make something called induction hypothesis. With this hypothesis, we prove the claim for the next value of n, which we call it as induction step. So we shall appreciate this by taking a specific case study or something that you have seen as part of your JEE preparation. So you would have seen this case study. The sum of first, say k natural numbers is precisely k into k plus 1 by 2, and k is at least 1. So what base case says is, verify whether the claim is true for base values of k. So k is equal to 1. On the left, you have LHS is equal to 1, and RHS is 1 into 1 plus 1 by 2, which is 1. And when k is equal to 2, and LHS is, you have 1 plus 2, which is 3, and RHS is 2 into 2 plus 1 by 2, which is 3. So this is our claim. Claim is the sum of first k natural numbers is k into k plus 1 by 2. We experimented with some values, and finally we arrived at this formula. Now we want to show that this formula is indeed true for any k. And to establish that it is true for any k, we want to use this technique. So as part of base case, we have verified for small values of k. For example, 1 and 2, we see that this sum matches this formula. So for base case, the claim is true. For base case, the claim is true. Then we have something called assumption, which is induction hypothesis. Okay, or inductive hypothesis. This is an assumption. Listen carefully. Assume the claim is true for k greater than or equal to 2. This value, where exactly the case starts, right? This should have been proved as part of base case. So k is at least 2 because for 2 it is proved. You can also assume k is at least 1 or k is at least 1. This value must be explicitly proved as part of base case. So must be proved as part of base case. So if you say the claim is true for k, where k is at least 2 or k is at least 1, this value, whichever value you mention, that should have been proved explicitly as part of base case. We will see why. Okay. Now assuming this, we will establish something called induction step. So to prove that the claim is true for k plus 1, what is the value of k? K is, if you are proved as part of base case 1, then you say k is at least 1. So what is that we want to show? We want to show that 1 plus 2 so on up to k plus 1 is k plus 1 into k plus 1 plus 1 by 2. This is what we want to prove, and what is given to us, or the inductive hypothesis says assume the claim is true for k. So which means 1 to k is k into k plus 1 by 2. Okay. Now how are we going to prove this? By inductive hypothesis, and by inductive hypothesis we know that 1 to k is what? 1 plus 2 so on up to k is k into k plus 1 by 2. Correct? Apply this. So you get k into k plus 1 by 2 plus k plus 1. By inductive hypothesis, we know that 1 to k is k into k plus 1 by 2. So you get k into k plus 1 by 2 plus this k plus 1. Correct? This k plus 1. Correct? Now if you simplify this, on simplification, what do you get? You get what we need. K plus 1 into k plus 2 by 2. With this, we conclude the claim is true for any k, k is greater than or equal to 1. But there are certain things which we will pay attention and discover that, or meaning the insights into the induction, and why is this technique so powerful? Is this assumption that we make, will this be true always, or can this go wrong? Such insights we will see now. Let me repeat this. It has got 3 components. One is the base case, wherein you explicitly prove for smaller values of k. Then you make an assumption which we call it as induction hypothesis. We say that the claim is true for k, and you fix a lower bound for k. The lower bound k is at least something. That lower bound we should have proved explicitly as part of the base case. And then we have something called induction step. As part of induction step, we prove the claim for k plus 1, and where k is at least 1, this 1 is proved as part of the base case. Then take the LHS, and you know that by induction hypothesis, we have assumed the claim is true for k, so this becomes k into k plus 1 by 2. So take that, add k plus 1, simplify, you will precisely get this. Now we will get into the insights. So we had something called base case. As part of that, we have established for smaller values, k is equal to 1 and 2 and so on. Let's assume 1 is done. Then hypothesis, we said assume the claim for k greater than or equal to 1, this value comes from the base case. Then we add something called induction step. As part of induction step, we gave a formal proof. So we gave the proof for k plus 1 and k is at least 1. Which means what? Is the claim true for 2? Is the claim true for 3? Is the claim true for 4? Such things we have established as part of this. Now listen carefully. When we said it is true for k is equal to 1, this one direct proof with no assumptions. So this is perfectly fine. Then we said assume the claim is true for k at least 1. And I said that the starting point should have been proved explicitly as part of base case. So then you come here. Is there an assumption here except the hypothesis? No. And except induction hypothesis, the proof did not assume any other fact or proposition or whatever. Okay, it did not assume any other statement. Correct? Now, or put it in other words, what is that we did? Assuming k is at least 1, we presented a proof for k plus 1 where k is at least 1. Correct? Now listen. Assuming k is at least 1. So assume k equals 1 and we presented a proof for k plus 1 which is 2. Now this one is a valid assumption because this is a valid assumption. Valid assumption because we have established as part of base case this cannot be wrong. Correct? So induction hypothesis, it is only offering a bridge between base case and the induction step. It's kind of a magic that is trying to establish the generalization, specific values to generalization, and keeping this as a bridge. Although this says assume the claim is true, this assumption can never go wrong because of this reasoning. So you assume k is equal to 1, and we gave a formal argument without any other assumption that it is true for k plus 1 equals 2. Okay. Now again look at this. It says assume the claim is true for k is at least 1. It could be 2. Now assume k is equal to 2 and follow this argument. We presented a proof for k plus 1 is equal to 3. Now we are assuming this. Why is this correct? This is correct because the previous induction step presented a proof. Assuming k is equal to 1, which is explicitly proved here, we have proved k is equal to 2. Now this is proved. Now I can assume k is equal to 2 and prove k is equal to 3. Now that 3 is proved, I can assume 3 and present a proof for 4, and it goes. So what is that we are doing? It's a kind of k is equal to 1 is explicitly proved. Assuming this, we prove k is equal to 2. Then this is proved now. Now I can assume this because it's a true assumption, and I prove this. Now it is proved, it's a true assumption. I prove k is equal to 4. Like that it goes. The claim is true for any k greater than or equal to 1. Is this fine? So that's the magic. Formally, what are we doing? We have something called base case, which I call it as P of 1. For k is equal to 1, we prove this. Then for all k is at least 1 and the claim is true for k, we present a proof for k plus 1. Correct? This is base case. Induction hypothesis implies induction step. Then we conclude, therefore, for all k is at least 1, P of k. Then you conclude, for all k, the sum of first k natural numbers is k into k plus 1 by 2. And formally, when you write, this is what we get. First order logic, FOL for the technique MI. It appears like a magic, but we are doing it in a systematic form. That's the beauty. Base case, assume the claim is true with respect to k is equal to 1. P could be any predicate. P could be the sum of first k natural numbers is this. So assume that is true with respect to base value 1. Then for all k is at least 1. Remember, this is precisely proved here. And assuming this, prove this. If P of k, which means if it is true for P of k, then we have a proof for P of k plus 1. And then this cycle starts. K becomes k plus 1, then k plus 1 becomes k plus 2, k plus 2 becomes k plus 3, and finally we conclude for all k, the claim P of k follows. That's precisely what we did over here. It appears like I am making an assumption as part of induction hypothesis, but that assumption is valid. It can never go wrong. It cannot be wrong because the lower bound as part of this is explicitly proved as part of base case. Then I run induction step. Assuming this, in a way you are only assuming this and proving this. Then for the next value of k it is proved. Then assuming that, prove the next value of k, and so on and so forth. So it appears like there is an assumption in between, but it is not. Okay, so that's the beauty of this technique. So this has got three parts: base case, induction hypothesis, and induction step. Induction hypothesis is acting as a bridge between the base case and induction step. And assuming this, we establish a formal proof without making any assumption as part of the proof. And then the cycle starts. And then base case goes into hypothesis, then you prove this. Once you prove this, that also goes into the assumption. With that you prove the next value of k, and so on. Finally you say this so and so claim is true for any natural number k. And this is such a powerful technique. Identifying the right base case and establishing a formal argument through induction step is a challenge as part of this. We will see a couple of case studies following this proof technique.